Thank you for joining us today from wherever you are around the world. We usually get a pretty good international audience. We're here in San Francisco at Predibase headquarters. We're excited today to host our webinar. Talk about some of the optimizations we've built into our fine-tuning stack. We've fine-tuned thousands of models built into our product, but I have my expert here, Arnav, who's going to talk to you about all those cool techniques, the impact they each have, and how you might want to think of them, with regards to your fine-tuning efforts. Let's go next slide here. All right, so quick logistics before I hand it over to our speaker here. Just a reminder, all lines are muted. The session today will be recorded. So if you need to drop early or you want to have a peer who you want to join the session at a later time, you can share the recording. Now, while the line is indeed muted, we do have interactive sessions here. And what I mean by that is please put your questions into the chat in the QA sidebar there. We will have some of our technical experts in the chat answering some of those questions, but also Arnav here, our speaker, will do a live Q&A at the end, during which you can ask your questions, and we'll get to the ones that are in the chat. We also have some polling questions, make it fun and interactive. You can answer those polls, see where others are on their sort of fine-tuning or LM journey. Take a minute, participate in those. We also shared some handouts today as well in the sidebar that you get the slides. We have a definitive guide to a fine-tuning ebook. So a few different ways as we're warming up here for you to get engaged. And then, of course, we do offer our platform. There'll be a little pop-up in the bottom there. If you're interested in trying it out, we have $25 in free credits for people who are joining today if they want to try fine-tuning Llama 3 as an example and serving it. So a few handouts and logistics there. With that, I'll introduce our speaker. So Arnav, go to the next slide. Awesome. So I can't think of a better person to lead this session today on fine-tuning sort of research best practices and things that we built, because Arnav is actually a senior ML engineer here at Predibase who's built much of our fine-tuning stack and has been at the forefront of fine-tuning thousands of models over the last year here as we sort of built out our capabilities, and is constantly up to date on the latest research. Obviously, he's building our fine-tuning stacks. He also participates in our open source projects, both Lorax and Ludwig. And prior to that, Arnav was at Lyceon, where he was building ML projects or products. So you have the expert here on fine-tuning. And with that, I'll pass it over to you, Arnav, to lead the session.
Yeah, thanks, Michael. And thanks, everyone. Good to meet you all virtually. And so just to dive right in, I guess the high-level agenda today is that we'll talk a little bit about the state of the GPU market over the last few years that may or may not have influenced your decisions on fine-tuning. And then we'll do a quick recap of how fine-tuning works and some common optimizations that people typically use when fine-tuning models. And then after that, we'll talk about the 9 steps that we took to accelerate our fine-tuning jobs that you should also be able to use, since most of them are out of the box. And finally, we'll discuss sort of next steps, things that are more forward-looking on how we can improve this further, and wrap up with a quick Q&A. Cool. So here, if you've been sort of keeping track of the market, since 2021, there's been a big surge in demand for GPUs sort of all across the world for a variety of reasons. The first is that we had COVID-19, which led to general global supply chain disruptions. And unfortunately, or fortunately, just depends, there's a lot of GPU production that happens offshore from the States, at factories such as TSMC. And so there was just a general decline in supply of GPUs available across the world. The second is that with the rise of crypto and crypto mining, there was, again, a big upsurge in GPUs because that's what helps with verifying transactions. And then the third, and probably the most important of all, over the last, probably since November 2022, is that since the launch of ChatGPT in November, there's a lot of companies that have more or less all enterprise companies have been accelerating their adoption of Gen AI applications, which means that they themselves need GPUs to either train or serve models for inference. And what's really interesting is that all of these sort of happen over overlapping periods of time. And the support from Tom's Hardware actually showed that there was sort of at the midpoint of 2023, there was a 52-week lead time to get high-end GPUs such as H100s and A100s. And so that's a long time to wait to get really high-end resources. And generally, like this limited supply of resources forced a lot of companies that didn't have access to these GPUs, as well as open source and general community users, to innovate, to make the most of the resources that they had. And in general, if you've been around in the fine-tuning world, it led to the birth, or I guess a recent resurgence of parameter-efficient fine-tuning methods across the industry. And LoRa was this big breakthrough moment where fine-tuning results were actually good, but it was really cheap and easy to train. And then for those that didn't even have access to really, like even medium-sized GPUs, the community came up, Tim Detmers and team, I think at Washington, came up with quantization, or QLoRa, which is a way to further compress your model, and we'll talk about it a little later, to train these models efficiently on GPUs as small as T4s, which are readily available for free, even on things like Google Colab. And so we at Predibase decided to sort of lean into this ourselves, given that we are built on top of open source projects, and we decided to implement the best optimizations that existed to make use of resources that users might have, and fine-tune large language models such as Mistral 7 billion on single GPUs as small as T4s. However, the great GPU shortage is now over, and what we've seen is that, in more recent times, over the last few weeks and months, that this large resurgence, this large shortage has no longer really exists, and there's approximately a 10 to 16-week lead time on getting these high-end GPUs, such as A100s and H100s for your Gen AI workloads. And really, what this means is, if you think about it, there was a good period for about a year and a half where resources were limited, and we forced a lot of innovation to do the most we could with those limited resources. But now we start to address the GPU resources problem, we can actually think about moving to a more efficient training stack, and so that's what we'll be talking about today. And the reason accelerating fine-tuning is important is broadly for two reasons. The first is that if you're able to train faster, that means you're able to get much faster iteration cycles on your training workloads. And so that means that you have a higher chance of getting to a better performing model that is production ready within the same amount of time. And the second is that if you're actually doing fine-tuning yourself using your own GPUs, then you know that GPU costs can be pretty exorbitant, especially if you're doing large-scale fine-tuning jobs. And so if you're able to accelerate fine-tuning speeds, then you can significantly lower your GPU costs, which is, again, really great for the business. So the webinar today is mostly geared towards figuring out how we can accelerate these fine-tuning jobs. But before we dive into how we can accelerate, it might be worth looking into how fine-tuning works once again. So traditional fine-tuning for any model, not specifically large language models, it follows this paradigm of forward and backward passes in deep learning, where you have a set of inputs, in this case for LLMs, free text, that gets tokenized and passed through the weights of the model, and then it produces an output, which is just the probabilities for the next token. And typically, once you do that, you compare it against the actual expected token, and you can compute a backward pass, which is essentially geared towards updating the weights in your model to minimize the error so that your model is learning and improving over time. And so that's represented with the delta W that you're seeing here on the right side. However, full fine-tuning is really slow and expensive. And the reason is that usually to do training, you need to keep track of activations, keep track of gradients, and keep track of your optimizer state along with the model weights. Each of these are pretty memory intensive in themselves. And when you start thinking about large language models, we've we've started hitting 7 billion, 13 billion, 70 billion, and recently even well excess of 100 billion parameter models, which means that you need a lot of memory to do these jobs efficiently. And let's say you're even able to do that. One of the big things that has come out of full fine-tuning is that a lot of these language models run into a problem called catastrophic forgetting, where the model forgets the general notions of semantics and language and grammar that it learned while learning your specific task. So that's not promising, especially if you're going to be spending a lot of money doing full fine-tuning. And sort of one way to make this work that we used, and this is great for low resource environments in particular, is this idea of parameter efficient fine-tuning, or parameter efficient fine-tuning, where you only train a small set of task-specific weights. And one common method to do that is called LoRa, or low rank adaptation. And the idea is very simple. You still have the same inputs, the base model, and will produce outputs, but you freeze the base model's weights. And instead, you just learn a small set of linear layers, LoRa A and LoRa B, that are basically catered towards your task. During the forward pass, your input is passed to both the base model weights as well as the LoRa weights, and then summed together before passing it forward. And during the backward pass, you only update the weights of the LoRa layers. So it's a lot more resource efficient than updating the weights of the entire model. And one thing that's really interesting about LoRa, in case you're unfamiliar, is that LoRa A and LoRa B are two linear layers that are individually very, very small. But when you multiply them together, they actually have the exact same shape as W, which is why they can be added forward. And these weights are usually on the order of 0.1% to 1% of all the weights in W. So very resource efficient. And one other advantage is that you only have to keep track of the gradient updates and the optimizer state for these trainable parameters. And in case you want to be even more resource efficient, about a year ago there was a birth of this idea called quantized LoRa. Neither concept was really new at the time, quantization or LoRa, but when fused together, all it does is that instead of it loads the base model's weights with 4-bit using 4 bits instead of 16 bits or 32 bits. And since base model weights are more or less 99% of all weights in memory, you can actually significantly compress the VRAM you need by a multiplier of 4x to 8x, depending on the precision you were training in before. And the only thing to call out is that the LoRa weights are still the same. They're still in 16-bit. And that's okay because you want higher precision so you actually get good performance. And they're, again, a very small fraction of the weights. And gradients are still only computed for the adapters. So at Predibase, we use a combination of we used QLoRa fine-tuning for almost all of our training jobs. And this let us run even pretty large models on just really small GPUs such as 810Gs. So very resource efficient. And then that begs the question, well, if all the optimizations we made till date were all geared towards trading off speed for memory, how can we actually now accelerate fine-tuning given that the GPU shortage is no longer a problem? And that brings us to the state of affairs on March 15th, earlier this year, when we decided that this is something we want to focus on. The bar graph essentially shows, this is just a small sample of the data sets we used, but the bar graph essentially shows 4 data sets that we wanted to benchmark performance on. And the current state of those benchmarks on March 15th. You'll see that there's 4 data sets of different sizes in terms of the number of rows, as well as the sequence lengths. And what you'll see is on average, most jobs took several hours to train. And larger data sets such as Magic Code and Drop, which are actually not very large, took on the order of multiple days, which made it kind of painful to iterate on for most of our users, but also internally as we benchmarked various things to understand performance. And so we decided the best way to go from here to the future end state, which is fine-tuning that feels really fast, is to follow a 2-step process. The first is to learn about the impact of all of the optimizations we built that would help us save memory and sacrifice speed, and unwork them one by one to basically speed up training. And the second is to build net new optimizations that are purely geared towards pushing training performance without affecting quality. And so when we saw this, I guess the first question I had was, well, we're running these on 810Gs. What if we just run them on A100s without changing anything at all? And so that was the first experiment that we did. And it turns out that in general, the hype around better compute is very real, right? A100s compared to 810Gs that we use, which have about 24 gigs of VRAM, A100s have 50% more tensor cores, about 2.5 can do floating point operations about 2.5 times faster compared to 810Gs, and also have about 3x the GPU VRAM, all of which are very desirable characteristics of any hardware. And just by making the swap, we saw that on average, we were approximately 1.6 times faster just by making the swap and keeping everything else the same. However, the one thing that is interesting is that you'll notice that the net impact of moving to A100 is disproportionate between different data sets. So larger data sets like Magic CUDA and Drop benefited a whole lot more from this jump, almost like a 2x improvement, if you will. But other data sets such as Vigo and Glue didn't benefit as much. And so we moved training to be faster, but some data sets, like these data sets, are still taking on the order of a day, which is far too much for a data set of that size. So what can we do next? Essentially, we decided to now take a look at the entire training process and sort of remove things piece by piece by understanding the implications of each of the decisions we made. And the first one that we decided to look at was looking at the optimizer of choice. The reason we decided to look at this first is because in the original QLoRa paper, the implementation suggests that using a page optimizer, which I'll talk about in a moment, helps prevent the effects of memory spikes by offloading the optimizer state from GPU memory to CPU memory. And the reason they said that this is okay in terms of performance hits is because in new NVIDIA cards, they use something called unified memory, where instead of data transfers happening from the PCIe bus to CPU and then to the GPU, you just have a direct shared layer where you can just change, like a pointer to say it's on CPU or on GPU, but the memory is sort of unified. However, paging is really expensive, particularly in cases where you have large data sets where each row is very long, because you actually tend to page your optimizer state from GPU memory to CPU memory and then back to GPU memory for each optimizer step that you take. And so what if we just went from page atom to atom? That already showed about a 10% improvement in time per step, which is a good proxy for saying how fast is training going. But we decided to take it a step further by also exploring this notion of fused optimizers. And we used fused Atom W, just Atom W for more stability, I guess, in training performance. But we noticed that compared to paced Atom, this is about 39 to 40% faster on average, which is a pretty significant leap in performance gains. And so to understand why fused Atom is so much better than Atom and paced Atom, it's important to understand how optimizers work, particularly Atom. And so with Atom, the way it works is that normally when you have you have parameters, you forward pass through it, and then on the backward pass, you'll compute the gradient with respect to the parameter weights and the loss. You'll update the moving average, which is a set of the moments. So the Atom, I'm not sure how familiar everyone is, but Atom has these two states that it maintains per parameter, which are the first and second moments. So it needs to update those moving averages. And then there's a step of bias correction to prevent wrong values. And finally, you update parameters. But it turns out the way regular Atom works is quite inefficient. And the reason is that it does each of these sort of element-wise operations, so gradient drop computation, updated moving average, and correcting moments, sort of like individually. So there's a lot of memory accesses that happen because of that. And in general, GPU memory moving data from slower parts of GPU memory to faster parts of GPU memory is very expensive. And the other unfortunate part is that the parameter updates themselves are not happen individually. So let's say you do this part of the computation, then you need to update these separately. And so it's pretty slow. But what fused optimizers offer is two big things. The first is that they have kernel fusion, where they group gradient computation, moving average, and correcting moments as a single operation, as opposed to three different read, write, and compute operations. And so this is significantly faster than doing it the traditional Atom way. And the second is that we use something called, not we, the fused optimizers use something called multi-tensor apply launch. And it's just a fancy way of saying that instead of updating each parameter individually, one by one, we can actually batch the actual updates once we compute the corrected moments or the moving averages that we want to use to update these parameters. So by batching the memory bound operations and then batching the parameter updates, you actually get a pretty significant lift in training speed. And so with that, so we've now changed our optimizer to fused Atom W. The next thing we should look at is batch size tuning. Now, one of the things we did early on is we decided to set a batch size of 1 and instead use gradient accumulation steps to scale up the effective batch size. And the reason we did this is because occasionally there were inputs that would show up in the training data set that were really long. And because computing attention is quadratic in terms of memory, assuming using flash attention 1, it would lead to ooms. And so the idea was, let's just use batch size 1 to give every row the highest chance of being using memory without running into ooms, and just use gradient accumulation steps. Now the problem is that this actually is very inefficient because it doesn't utilize the GPU to its full capacity, particularly the aspect of parallelization that GPUs offer. And so what if instead we could be a lot smarter than that and implement a batch size tuning step before training that tries to find the maximum number of tokens that will fit before we hit an out of memory error. So now we know the maximum number of tokens that we can do in any given forward and backward pass. And now using that, we can dynamically create batches where you can keep inserting rows into the batch till the total number of tokens across the samples in the batch is less than this theoretically maximum value. And so you can modify your data loader to actually be implemented in this way. And so what you end up seeing is two things. You get much, much higher GPU utilization, right? Like we're close to hitting like max in terms of GPU memory. In terms of operations, we're at 98 to 100% almost all the time since we're pushing the amount of parallelization. And in general, depending on how much you're able to push through, this is a simplified example, but depending on how many samples you're able to pack, you can see anywhere between 30% and 40% or even higher performance improvements. And it's all because of parallelization. And one reason, in case you're curious, like if I was to go from batch size 1 to batch size 4, why doesn't my speed increase by 4x? The reason is that there's sort of some limits to the amount of parallelization a GPU can do. And also a big thing is that, there's a big factor in this is also memory bandwidth, which is how quickly you can load things into memory, push things through, and then do those updates. And that becomes the bottleneck at that point. Cool. The next thing that we used to do with the Ludwig framework is compute a lot of different metrics. So everything from loss and perplexity to root scores and blue scores and character error rates and word error rates, just a whole slew of metrics. But it turns out that in practice, with fine tuning, loss and perplexity are usually a pretty good proxy for how the model's learning process is going. And it's really hard to gauge the numeric values of blue and root score just from training data. Instead, those metrics are better if they're computed post-training on a custom data set, let's say for summarization. And also these metrics aren't really good for all use cases. But what's really interesting about them is that they're actually very expensive to compute. So depending on the number of tokens in your training data set, the cost of computing something like a BLUE score or a Rouge score is actually quadratic in nature. And it scales quite a bit as you go to larger and larger context sizes. And at Predibase, what we used to do is we would compute evaluation metrics on every checkpoint, which would be every 1,000 steps without not factoring gradient accumulation. And then we reported these metrics on a validation split and on a test split. So we did it twice per checkpoint. And if you think about this, let's say the average data set has about 2,000 tokens or maybe even 1,000 tokens. That's about 36 seconds for every checkpoint, or a minute spent just computing BLUE and Rouge, forget everything else as well. And in case you're curious as to why it takes time, it's because of how these metrics work, where they compute n-gram combinations of different sizes, and computing n-grams and comparing n-grams is definitely an expensive process. So we decided to more or less disable most of our evaluation metrics and keep it to just loss and perplexity, since they were most meaningful and very cheap to compute. And finally, the fifth thing we did, which is again an optimization that a lot of people use in environments where you don't have enough GPU resources, is this idea of gradient checkpointing. And in case, just to explain what's going on here, in traditional deep learning, you have a forward pass and then you have a backward pass. And in the forward pass, as you see here, we save the activations from each node or each parameter. And then during the backward pass, we actually update the parameter based on the loss and the activation, and then propagate backwards. However, this means that you have to always store these activations in memory, which means you need, and it can be pretty large depending on sequence length and the size of your model. And so that's actually desirable in the desired state we want to be at. But what we were using was gradient checkpointing. And the reason it was really useful is that you can essentially, every square root of n nodes or layers, you can checkpoint those activations and forget everything else in between. And when you need to compute the activations again, you can just forward pass from the checkpoint to the next few, layers, then compute their losses, update those parameters, and then forget the checkpoint. And so effectively, what you're doing is 2 forward passes and 1 backward pass for every step, which is definitely more memory efficient because you scale down memory by almost the square root of n in terms of the amount of memory you need, but it slows down training by 25 to 35% in practice. So these are a lot of things that we had implemented, improved, or fixed so far. And to just take a bit of a pause, let's talk about what combining all of these things, isolated things, means together in practice, right? What we found, so far we have bad size tuning, no more gradient checkpointing, using a fuse optimizer, disabling expensive text metrics, and I'm missing something. But with all of those, what you'll see is that compared to just, and also using A100s, we're able to bring down, improve training time from our beginning by about 3.7 times faster. And that's definitely a lot faster than just using A100s by themselves. What was also really interesting is if you break this down a little bit further, we saw about a 5x improvement for longer data, or for data sets with more rows, so magic CUDA and drop. But slightly slower training still feels counterintuitive for smaller data sets such as Vigo and Glue, where I think parallelization effects aren't as significant, although Glue does show a pretty significant 6x drop right here. So can we do even better than this? And this is where we can start getting into micro optimizations that will all help improve training throughput. The first of which is this idea of loading pre-quantized weights directly into memory. So at Predibase, as I mentioned earlier, we do quantized LoRa-based training. And traditionally, the way quantization works is that you download the partition weight files serially, so one by one to disk, and these weights are in FP16 or BF16. Something like a Llama 3 8 billion might have 4 partitions, each of which are 5 gigs in length. So right away, you're bottlenecked by the network bandwidth that you have. Now let's say these weights are loaded, are on disk. The way it works is that the way quantization works is that you load a layer into CPU memory. you compute something called quantization coefficients, which are basically a way of mapping the data back from quantized state to floating point state, and doing that interchange. And then you quantize, using these quantization coefficients, you quantize the weights on the fly by converting them into uint8 representations, and then placing them on the GPU. So that involves doing a malloc, allocating memory, pushing the weights in there. And you do this for every single layer in a loop, more or less. I think you can parallelize it, but it's generally pretty slow. And then you finally get your quantized model. And for Llama 3, 8 billion, on a T4 that takes about 73 seconds, assuming the weights are already on the disk. So I'm not even adding the cost of doing this operation right here. But in more recent times, I think Bits and Bytes and Tim Detmers and Hugging Face together have worked on enabling this idea of loading pre-quantized weights directly. So what if you did this aspect ahead of time, save these weights, and then pull these weights when you actually want to do training? And the advantages is manifold. The first is that you only have a single partition of weights. That's about 6 gigabytes of memory. And it has tensors that are FP16, BF16, and uint8, because not all layers are quantized. And then you can actually load this directly into GPU memory instead of actually having to compute these coefficients and quantize everything. And because the metadata with which these weights are saved already have the quant state and the coefficients saved as part of it. And so that can bring down your load time by about 3 to 4x, assuming you're not even downloading weights. But I think if you download weights, it's well above 4x faster, depending on the model size. So larger models will benefit from this even more because quantization on the fly is very expensive. The next thing we can do, or the seventh thing that we can do, is use this notion of sample packing. And the idea in some ways is very similar to batch size tuning, but it takes it a step further. So with batch size tuning, like I said, you may end up in a case where you've packed as many tokens as you possibly can, right? But what if instead you were to pack all of that into a single sample and increase the number of samples that you can process in parallel? So the idea is very simple. Imagine I have 4 rows in my training set. So it's an apple a day keeps a doctor away. The quick brown fox jumps over the lazy dog. Another sentence right here. We can actually fuse these into a single sample and separate them using BOS tokens and EOS tokens, which I've highlighted in purple here. And you can keep packing these samples into a single merged sample until you hit whatever desired max sequence length you have. And then you can do this for multiple samples in your data set. So you're effectively compressing. So now you're going to benefit from 2 things. You're going to benefit from batch size tuning, which is what is the largest number of max sequence length tokens that you can push through. And the second is how many of these can you push in a single forward and backward step. And so very simply put, by doing this kind of optimization, you can train 2x to 5x faster because you're compressing the number of samples you're training. You're still training over all of them, just in a much more efficient way by utilizing your GPU to its maximum capacity. And you do have to do some pretty smart things to make sure that loss is correctly being computed and that sequences aren't attending to sequences they're not supposed to. But that's more on the quality side and not something we're discussing today. Another thing that has become really big and probably everyone's heard of is flash attention, and more recently, flash attention 2. And I think it's really important to take a moment to understand what it does and why this helps so much. So let's ignore this part of the diagram for a moment. The idea behind flash attention 2 is very simple. So traditionally, when you're doing attention computations, if you think about it, the first thing you do is you multiply the query vector with the key vector. So that's a matmul. Then you mask it to make sure that tokens only append to tokens that come before it, because most architectures use decoder only. Most architectures today are decoder only architectures. Then you might apply a softmax operation to actually compute like the probabilities of the attention scores. You might do a dropout, and then you do another matmul with I guess like the value tensor, and that's how you basically get like attention, right? But most people tend to optimize the multiplications, and if you think about what A100s do as well, I mentioned that they can do more flops per second, which talks about this aspect. But if you actually break down the time spent doing a single attention computation, the most of the time is spent not in the matmul ops, but actually in the masking, softmax, and the dropout ops. And what's unique about them is they aren't compute bound operations. It's their memory bound operations because you have to access individual elements in memory and update those values. And so the idea of flash attention is, can we actually make our attention mechanism IO aware or memory aware and be smart about reducing that? And what flash attention does is it proposes a fuse kernel, which basically condenses all of these ops into one single op, more or less. And that is significantly faster than doing these individually. And before I talk about how that actually works or what that looks like, in general, we've seen flash attention to anywhere between 3x and 8x faster than baseline eager attention or baseline vanilla attention. Just depends on the data set, 8x to 10x faster. And what's really cool is because of the way they've written this kernel, probably an unappreciated benefit is that it drops the amount of memory you need from quadratic to subquadratic or near linear. That means that you can actually fit even more data into your GPU memory or fit even longer sequences into GPU memory, both of which are great for all the other optimizations we talked about before this. And the last part is that the attention scores are still exact. There's no approximation. So it's very nice. And the thing that I did want to bring up is now on the left is a really good example of how GPU memory hierarchy is built out, where you have main memory, which is like CPU memory, right? Has DRAM, which is pretty fast in itself. But then you have GPU, like I think it's called high bandwidth memory or HBM, which is a tier above. It's a lot faster. But the issue is that as you go higher up in the memory hierarchy, you actually, the amount of memory capacity that layer has, if you will, is much smaller. And then you have GPU SRAM, which is, almost as you see here, like 20x, 10 to 15x maybe faster than GPU HBM. But instead of 40 gigs of memory, it can only hold 20 megabytes of memory. So extremely small, but very, very fast. And we would generally benefit if you were able to push as many computations into SRAM. And also we would benefit if we were to reduce data transfers between HBM and SRAM. And so that's generally the idea of what flash attention is doing. The way traditional attention works in GPU memory, this is very simplified, but you have since SRAM can only hold 20 megabytes of memory at a given time, you need to load it. Like these tensors are usually loaded in blocks from HBM into SRAM. You do a computation and then you write it out. So you can do this to compute, query times k, so key. You can do this to do the masking, and you can do this to compute softmax, and then you can do this to compute matmul. But in each step, the issue is that because of how SRAM is designed, you need to read a small chunk, do a computation, and then write it back to HBM. And the read and write operations are really expensive and what are essentially like IO bound operations. What flash attention does is that it's IO aware, and it does two clever things. It reorders some of the operations in traditional attention that are more, I guess, that are smarter, and it removes all of the redundant HBM reads from HBM to SRAM and writes from SRAM back to HBM. And so what they do is they shuffle up things a little bit where they, I don't know if I have this right, maybe I wrote this wrong, but the idea is that you actually load the K and V blocks into memory, and then you iteratively load blocks from the query tensor, compute attention, compute, I guess, like the matmul computer mask. And instead of computing attention, what they do is very interesting. They compute softmax statistics, which is sort of like a summary of the distribution so that you have that information. The reason they have to do that is because you can't actually do a softmax operation unless you understand what the denominator needs to be, because that's just how the softmax function works. And so they do this iteratively. They write these masked blocks back into SRAM. And then by the time they do this full loop of flash attention, they have two loops that run. The final sort of statistics actually has the exact value of what it needs to use to compute the denominator. And so it's able to just do exact softmax at the end of these mini computations, but it reduces reads and writes significantly. So yeah, significantly faster than using traditional attention. And if that was not enough, we decided to go a step further, and we use optimized CUDA kernels for LoRa fine-tuning. Without going too much into the details, we have CUDA kernels that do fast quantization, fast dequantization of quantized linear layers. We have CUDA kernels that do fast cross-entropy loss computations. There's some methods that do efficient forward and backward multiplications that are mostly focused on computing attention of QKB and with the LoRa layers, because that's usually where the LoRa layers get injected. And most of these are optimized for BF16 natively in the hardware for two reasons. Generally, these kernels show a pretty significant speed up when you use BF16. And the second is that BF16 is shown to be a lot more stable in terms of training and quality compared to FP16, because of the way the exponent and the mantissa are arranged. And one more reason is just that, when you do mixed precision training, you have to do something called gradient scaling to prevent overflows and underflows, but BF16 doesn't suffer as much because it has a much higher range. And so with that, if we were to combine sample packing, flash attention, and CUDA kernels, you'll see that there's two things that we gain more empirically beyond the paper. The first is that the amount of GPU memory. So on the left, the amount of GPU memory you need drops significantly by about 66 to 70%. And in fact, when you do sample packing, after you drop it, you can actually maximize your GPU utilization because you're pushing as much data through during training as you possibly can. And on the right side is the time taken per step. And what you'll see is flash attention 2, because attention computations are no longer our bottleneck, because flash attention 2 helps solve that pretty significantly. It already improves the time per step by, I think, what is that, like 20 to 25%. And then if you also include training kernels that help reduce the memory bound operations and fuse them into single kernels, you again benefit from the same reason that flash attention does, which is fewer read and writes from SRAM. And so we end up with 58% lesser time spent per step. And with all of these optimizations, sort of at the end of 2 weeks of diving deep into the weeds here and benchmarking, we end up in this spot where we've cut the time for example, Magic Coder from almost 3 days to just about 6.5 hours. The same is true for Drop, where it's dropped by, again, like about a 10x improvement. And certain data sets, such as Glue and other data sets with similar properties, actually benefit even more by seeing like almost a 36 time speed up. So you've gone from something taking almost like, what is that, 12 hours to 20 minutes, which is a pretty significant improvement in training speed and throughput. And same with Vigo. And I have like a couple of data sets here, but across all the data sets that we had internally sampled, on average, you see about a 15x speed up compared to what was there before. Just depends on the data set. And that's where we were at the end of 2 weeks. That's how we got there in 15 days, by unworking things that were more focused on resources as opposed to speed, and then building in some new things or adding new things to our stack that are open sourced that help push performance through. And really, like, where do we go from here, right? Training's already 10 to 15 times faster. Iteration speed feels really good. Things feel snappy. Well, one thing we can explore is pushing this further by actually moving to H100s. And we did benchmark this ourselves internally and saw that, you actually get another 2x speed up at almost minimum across the board. But the reason we may not want to use H100 is because they're better served for inference than they are for training. That's up to us. It's just an internal decision. The second is that one of the things that we do, as I mentioned earlier, is do quantized LoRa training. And quantization, even if you use preloaded quantized weights, is still very expensive because you have these operations where you have to scale quantized weights back to dequantized weights, do a matrix multiplication, then quantize them back to their quantized state. And that process, if you do that every single time, you have to do a forward pass and a backward pass. So extremely expensive to do. And with all the other optimizations we've built in, it turns out that we can actually more or less get rid of quantized LoRa training and just do LoRa-based training for models that are under 20 billion parameters and still do it in half precision. So that should actually be a pretty significant performance boost just by using non-quantized LoRa as opposed to quantized LoRa. And then let's say, I think at some point there's diminishing returns on pushing training speeds further. But instead, what we can do is be smarter and think about how training can help influence inference speeds, and working on mechanisms to train special weights along with LoRa that improve inference throughput by 2x or beyond. And you'll hear more about that in the coming weeks. All of this is possible through two open source projects that we maintain, Ludwig and Lorax. Ludwig has almost 11,000 stars now, and it does LLM fine-tuning, but also other things such as general multimodal deep learning. And Lorax is a new open source project that we started in 2023, which has about 1,500 stars, and it's one of the fastest growing GitHub projects out there, probably behind Karpathy's C++ Llama implementation. But and feel free to check these out. So you can go to ludwig.ai to get set up. You have LoRaXchange.ai, which talks more about Lorax, and Lorax is our serving solution where you can serve hundreds of LoRa's on a single GPU with virtually no inference degradation when you're swapping between these LoRa's per request. And really, we've built in all of these optimizations that I talked about today into the Predibase platform. You can bring your data set, you can customize it through Ludwig and our internal fine-tuning stack. You can collaborate with users, create different versions, compare different adapters, see metrics, and iterate on them quickly with faster fine-tuning. And then you can serve it at scale in a cost-effective way using Lorax, our open source serving repository. And all of this is possible by either deploying in our cloud, which you call Predibase Cloud, or in your cloud, so VPC. And we are SOC 2 compliant, and you get full ownership of your data and models. What's the time? Maybe what we can do is I can show you a quick example of what fine-tuning looks like within the, okay, one moment. Let me just sign back in. Okay, so let me show you maybe of an example of what fine-tuning looks like in the Predibase platform. And it's really, really quite simple. We won't go through all the steps, but all you need to do is install the Predibase SDK. Get your API token, which you can get from within the platform. Right here, right? Copy it, and then all it requires is grabbing a data set, which you can use anything really. We do instruction tuning at Predibase, so for now, but we're adding other things soon. You upload your data set, you create a repository. Think of this as a GitHub repository, but for adapters where you can track experiments and changes over time. And again, it uses a YAML-based config, so you can see and easily track changes that you've made across versions. And then all you need to do is call predibase.adapters.create, and you pass in a fine-tuning config that has a base model, your data set, your repo, and maybe some description describing, like a commit message almost. But we also offer, customization of a lot of these, a lot of the training parameters, so epochs, rank, learning rate, what LoRa modules you might want to target. and so on and so forth. And yeah, you get, as soon as you do this, that's about it. We'll figure out compute and train your jobs as fast as we can, using all the optimizations we talked about today. And then you can monitor training progress and then serve them with LoRaX in a pretty lightweight way. So with that, I'll pause. I think that more or less brings me to the end of the webinar itself. Let me see. Yeah. And yeah, if you want to check out Predibase, yeah, go to pbase.ai/get started. We offer $25 in free credits if you just want to take a spin, take fine tuning for a spin, or take inference for a spin, or both. Yeah, we make it extremely easy to do that. And yeah, with that, maybe we can do Q&A.
Yeah, great. So first of all, folks, if you're still on, you can put additional questions in the chat, and we're happy to answer them live with Arnav. I know many of them have been answered. We can cover some of them and just already covered Arnav, and if more come in, we'll jump on them. So first of all, someone just asked, if you train models in Predibase, can you export them?
Yep, we allow exporting models. Today we export just the final or the best weights for your model, but in the future we might also add support for exporting checkpoints should you want to benchmark each checkpoint by yourself.
Got it. And then if you are training adapters and want to retrain them, can you do that within Predibase with new data? Like, what's that process?
Right. So today we don't have that process baked in natively into the platform, but it's something we're definitely looking to add support for. Not only to be able to retrain adapters that you might have already trained with fresh data, but also to be able to train adapters for like a specific data set, and then use those weights, but then augment it with a different set of LoRa weights for a new data set that you might have.
Here's one that just came in. I don't know if you have a perspective on this, Arnav, if you've done the analysis,
Yeah.
but is there an impact, from input length on training and inference latency from your experiences?
Absolutely. So input length in general, there's a few factors that affect training. One of which is definitely input length, because it means that the attention computations become more expensive. But what's really interesting is it feels a whole lot less noticeable with flash attention too, because it does linear, like the cost of bringing attention is linear instead of quadratic. Even then though, on training, there's definitely a significant impact. And on inference too, I would say that the most expensive part about a long input length is the pre-fill stage. So the way inference works is that you have a pre-fill and then a post-fill or generation step. And pre-fills can be a lot more expensive if you have a very long input length. But again, with flash attention too, it feels a lot less noticeable than it used to feel prior to that.
Got it. Here was a question earlier. I'm curious your perspective on this. So someone mentioned that they were using like Hugging Face's transformer library for PEFT and LoRa. And they were curious like what you would see as like the advantage of like using a Predibase as an example to do like fine tuning other tasks. How do you see the value?
Oh, that's a great question. So there's a lot of things that we built in, some of which are really efficient batch size tuning, which is one big one where we try to push GPU utilization as much as possible. But let's even say like with Hugging Face and PEFT by itself, you could train. There's a lot more to training than just the training process itself. You need to have mechanisms to efficiently detect when out of memory errors are going to happen, recover from them automatically, make smart adjustments, essentially building in redundancy and fault tolerance into your training pipelines, which happens more often than a lot of people think. And so at Predibase, we've already smartly built that so that your training jobs succeed as almost all the time. There's always edge cases. So you're coming to Predibase for the stability of training, the speed of training, and the third thing I would say is one thing that I think that people might underestimate, but it's very important, is you can train quickly, but that's half the battle. You also need to have really high quality models that you can actually put in production. And we've fine-tuned thousands of models at Predibase and learned really smart combinations of hyperparameters that actually push performance quality to be pretty much best in class. And that's something that we bake in almost natively into the platform as well. So you benefit from all the experiments that we learn as we keep trying to improve model quality out of the box.
I thought, obviously, love this comment Lindsay shared. If you can get 50 times more efficient versus learning how to like pieces all together, why might you do it on your own? You could definitely do it on your own. I think that's why we're sharing today. But Lindsay also brought the point like, hey, 50 next day. What about 3 months from now? What do you think 3 months from now will be 40x?
It can definitely go faster. There's still a lot of things that we're working on or we've thought about but haven't implemented. And it's something we certainly can. And there's at least headroom for another 2x to 4x improvement from today without a lot of work. So, yeah.
So another question, is there such a thing as too many instructions in fine tuning, or will the adapter overfit if tuning an LLM with too large of a data set? Any thoughts around that?
Yeah, it's again a great question. So in general, autoregressive models tend to overfit, or they like overfitting. And larger data sets, I think there's a point of diminishing returns with larger data sets, where if you train them for too long, then they overfit. But again, at Predibase, one thing we do pretty smartly is we've built in early stopping mechanisms that smartly detect when loss has stopped improving after a certain number of checkpoints, and actually early terminates your job so that it doesn't overfit, or at least tries to reduce the chances of overfitting.
Nice. So, and just mentioned at the end, I know it's about fine tuning. Curious about how you think about optimizing inference. I will say there's something incredibly exciting that we'll be talking about very soon. In fact, our next webinar will be on some of those like cutting edge inference or optimizations we're doing. So stay tuned. And maybe you want to give a hint to that, Arnav, since you'll probably be on that one too.
I'll give a hint. In general, there's sort of two ways to go about improving, three ways to go about improving inference speed, right? There's using optimized kernels for inference. So that's one common path. There's using mixture of experts, where you benefit from the quality, but you benefit from the sparsity at inference time. And the third sort of area that's becoming pretty big is this aspect of speculative decoding, where generally in autoregressive models, you produce one token at a time. But what if you could do something really smart and generate up to n look-ahead tokens at each generation step? It basically means that your training inference improves by a factor of n. And we're working on some pretty smart optimizations internally as part of training that will help improve inference speed for fine-tuned models in particular.
Very cool. Maybe one more question. Joe had asked, any opinions on that we have on quantization approaches, GPTQ versus GGUF versus AWQ? Do you use any of these or something else? Thoughts on that?
Yeah, it's a great question. So we don't use them for training because they are post-quantization training methods. But in general, what seems to be most popular, both for inference, but also people tend to train on these a lot, is AWQ. It seems like AWQ, if I remember correctly, helps fix a lot of the issues that GPTQ has, and it works really well out of the box. And it also lets you control bits to like very specific levels, which is pretty nice. I haven't played around too much with GGUF. I just know that most people use GGUF to run LLMs locally. Not something that I've actually tried, but I think for production settings, AWQ is great for two reasons. In general, it seems to be pretty good, even if you want to fine-tune a post-quantized model. And compared to other quantization methods, at inference time, it takes the least performance hit.
Awesome. So I know we're at the end of the hour here. Apologies, we didn't get to all the questions. A lot were still coming in. If you do have a question, you can feel free to email me or Arnav, both just our names at Predibase, or support@predibase.com. Happy to answer them. But big thank you to everyone for joining today. We hope you found the content interesting and valuable. We had our professor here, Arnav, going deep dive in all the cool techniques. And of course, please check out the platform. We have $25 of free credits that allows you to fine tune and serve a number of open source LLMs like Llama 3, and you can go have fun with them. So thanks again for joining us, and we look forward to seeing you on our next one. Take care.